Singer from North Carolina State University, and he will speak about consistent systems of linear differential and difference equations.
Well, thanks for inviting me. The title is kind of boring, so I promise you there'll be more interesting things to come. But let me tell you how this talk is going to go. So I'm going to start with discussing an application of what I'll talk about. So I'll talk about the application first. And then the application involves questions about functions of one variable that satisfy both a linear differential equation and a linear difference equation, or perhaps two difference equations. So I'll talk a little bit about that. And now this is joint work with Reinhard Schäfke, and we've developed an approach to this problem that's a little more general. And so that'll be the third topic. And then this will I don't think I may prove something, but in the fourth part, I'll actually give you a glimpse of the proofs, and then what this has to do with Galois theory. In fact, the Galois theory was my path to it, but as it developed, it became clear it had other applications. So automata theory. So let me give some background. We have various models of computation, and one's always interested in how powerful they are. So for instance, you have Turing machines. Turing machine, it's a machine, it has internal states, there's a tape, it can read, it can write, it can move the tape back and forth, and it can change its internal states. And you could measure its power by asking, well, what sets of integers would it recognize, right? And so for Turing machines, the set of integers that it recognizes are the recursive sets. The sets of, well, it's not going to define them, but it's the sets whose characteristic functions are recursive functions.
That is the definition.
Okay, one could measure. Yeah. Yeah, okay. So one could look at weaker models. So the Turing machine, it had this tape, it moved back and forth, it could read and write. You could just say, I just will allow the machine to read, not write. And it just has internal states. And the tape moves in one direction. And that's the definition of a finite automata. And I want to talk a little bit about those. So let's see. So finite automata, you start with a finite alphabet, for instance, 0, 1. And you can form words on that alphabet. Those are strings. And now an automaton, I described it as a machine, but the best way to think about it is as some kind of a program, and the program is represented by a graph. The graph has some initial states where you start. There's some internal states, and there are things called final states. And no matter what state you're in, on your tape, if you see a symbol, you have instructions that will tell you, go to this other state, stay in the same state, or whatever. Okay? So here's an example. The initial state, you can think of the machine starting there. If it reads a 0 on the tape, it stays in that state. If it reads a 1 on the tape, it goes to this state called F, which is a final state. And then it moves and reads another symbol. So let's look at this a little more. I want to know what words are recognizable. So I'm thinking of this automata, and let's say I'm looking at this word and I read it from right to left. So I'm in my initial state, I see 0, I stay in the initial state. I move over, I see 0 again, I stay in the initial state, and then I see 1, and I go to this F, the final state. Okay? With this word, I'm in my initial state, I see 0, I stay there, I see 1, I go to F, and then I see 1 again, and I go to H. And notice that when you're in H, That's it. You're not going anywhere else. Okay? So this is what a finite automaton does. And I said I want to measure its power, so I want to talk about recognizing integers. Now, with Turing machines, it turns out it doesn't matter. You could write them your integers base 2, base 3, base 10, doesn't matter. A set is recognizable independent of its the base you write it in. But here there is a problem. So we talk about an integer as being k recognizable if you can construct a machine using this alphabet so that when it reads that integer, at the end, it's in a final state. Okay? So something is recognizable. This guy was recognizable, but this guy wasn't. We ended up in F here, and here we ended up in this H. If you think about this for a second, this finite automata recognizes powers of 2. So a power of 2, base 2, it's a bunch of zeros and a 1. If you have anything else in there, if you have 2 1s appearing anywhere, you're going to end up here. So this is a finite automaton that recognizes the set of powers of 2, base 2. And the question is, what happens if you write them base 3? Can you make a machine that will recognize powers of 2, base 3? And the answer is no, and it's a famous theorem. It's Cobham's theorem that says if you have 2 multiplicatively independent integers, multiplicatively independent means no power of one equals a power of the other, unless the power is 0. Multiplicatively independent. So if you have a subset of the integers that's both k and l recognizable, it's ultimately periodic, meaning something's in the set. If there's a period c, so that something's in the set, then c plus it, 2c plus it, and so on are in the set.
I think on your slide the period is d.
Excuse me?
On your slide the period is d,
Yeah.
and c is where it starts.
Right. Ultimately, periodic means it's eventually something's in the set if and only if we add something, this fixed number 2. Now, the powers of 2 are not periodic, right? We can all agree on that. So the powers of 2, you can recognize them, you can 2 recognize them, but you can't 3 recognize them because of this. And this is a theorem from the 60s. Let's see, in Eilenberg's book, he says the following: the proof is correct, long, and hard. It is a challenge to find a more reasonable proof of this theorem. And since then, there have been interesting proofs. There's one by Michaud and Villemarie, I don't know if I pronounced this. Vilmer. Yeah, that this question is related to things that are definable in Pressburger arithmetic. And something turns out to be k recognizable if there's an extension of, there's a one predicate extension of Pressburger arithmetic in which it's definable. And so it's a nice proof. There are other proofs. The original proof is a lot of combinatorics. And I'm not sure I understand it. Okay, so what does this have to do with differential equations, you ask? And I'll tell you. So one can look at the generating function of a set. So I have a set. I'm going to form a very simple generating function. I'll put a power of x in this sum, if and only if that power is in the set. Okay, so it's a generating function. And if a set is k recognizable, then this generating function satisfies a recurrence like this. Now, it's not a Q difference equation or a shift difference equation, but it's a difference equation of a kind. So you replace x by a power of x. And this looking at these things, I guess it was introduced by Kurt Mahler, and so it's called a K-Mahler equation. So here's the connection. It's not an if and only if statement. You can get things that satisfy K-Mahler equations. I think they know the condition, but I don't remember. Okay, so that's the connection. And there's a theorem that I'd like to mention by Adamczewski and Bell that says something about these K-Mahler equations. And gee, it has the same flavor, doesn't it? You have K and L multiplicatively independent. You have some power series that satisfies an equation like this with respect to K, with respect to L. Then it has to be particularly simple. It has to be a rational function. And you would think, gee, there should be a relation. And in Adamczewski and Bell's paper, they say, yeah, there is a relation. You can prove Cobham's theorem from this theorem. And I'll do the proof because it's nice. They regrettably say that in their proof of this result, they use Cobham's theorem. So you can just see they wish they hadn't. Okay. So let me prove this. The proof is simple, and at least you'll see what's going on. So which board should I write on? This one. So I have my set, and I form my generating function f of x, which is this just next to the and is in my set. So I have, if the set is K recognizable, then there's some x to the K to the I 0, L recognizable, the same thing is true. That's from this proposition that I haven't proven. So now F is rational. That's what the Adamczewski-Bell theorem says. Okay. So let's write this out. I can write Q of x times summation x to the m equals P of x. Now equate powers of x. And in general, so let me just do this in general. I have any kind of a power series. After a while, you're going to get a recurrence on these C's. Let's think about it a second when you equate powers. So you're going to get something like alpha n plus 1 an, this is C. Notation right. This is plus I. This will work for I. An minus 1 C n plus n minus 1 plus A0 C sub I. So you get a recurrence. These are fixed numbers, constants. Now all you have to think about is, in my particular case, the coefficients are zeros and ones. There are only a finite number of strings of length n of zeros and ones. Eventually, you're going to start repeating yourself. So, and then you're going to keep repeating yourself every so and so many times. So the ones will appear periodically, and that's what complex there is. Okay? So that's the relation. And so recently, Shefka, using tools that we developed, we refined them quite a bit, proved this Adamczewski and Bell theorem without Cobham's theorem. And I want to discuss the philosophy behind his proof and the other stuff that he and I have done. You know, so this will appear in a paper we're writing, but it's really so nice. Everyone should know that it's Shefka's proof, also in case it's wrong. So it's a new proof of Cobham's theorem. Okay, so I hope I've convinced you that it's interesting to ask the question, what happens if a function or power series satisfies two linear equations with respect to two different kinds of operators? So that's what I want to talk about now. So I'm looking at two linear equations. These D's will be some kind of operators, either a derivative or some kind of endomorphism or automorphism or something. And it turns out there's been quite a bit of interest. Can we read it? Yeah. So in 1992, Ramis looked at when one of the equations was a differential equation and the other was a Q difference equation, where here I allow Q to have absolute value 1, but I don't want it to be a root of unity. And again, if you start with a formal power series, satisfies one variable, it satisfies a linear differential equation, a linear...
Do they have the same order?
No, they don't, but you can always make them that way. Okay. Sorry, I didn't mean to give that impression. So when this happens, again, your power series represents a rational function. And the proof is using asymptotics. Let's go on. So Bézavin, in 94, the proof that's kind of similar to Ramis's proof, I think, that's my feeling, looked at this Mahler operator. I'm going to call these things where you take x and raise it to a power, and a differential equation. The reason that Shefka and I got interested in this was this case, and I wasn't able to find somebody else who proved it. So maybe, I don't know, I've looked. So it's with respect to the shift and with respect to the derivative. And, you know, the shift looks a lot simpler than the multiplying by q or raising to a power p, but believe me, it's a lot harder. Yeah, it's harder.
May I just, that's a second. For the third line, is it why is just the powers of negative powers or just negative powers and positive powers?
Question.
Sorry, because the conclusion
so
is.
this comes up with something that Julien said. In the first two cases, these operators actually act on this field.
Okay.
But replacing x by x plus 1 isn't going to leave you inside that field.
Okay, right.
But it will leave you inside this field. So you have to work it out, but if you
Really?
send...
Oh, okay.
Yeah, so 1 over x plus 1 is really 1 over x divided by 1 plus 1 over x.
Oh, okay. And that's how you get that conclusion. Okay. I thought it was...
Thanks for asking.
Right.
So there are more results along this line. So you can look at two shifts, and that's been looked at. Two Mahler operators, I said that was Adamczewski and Bell. Two shifts that are independent. I don't want I mean, if you pick an alpha that's a rational number, you're really not doing so much different. One can look at meromorphic functions. That's been looked at. There's a star here because these guys only looked at entire functions. More. Since here, I've assumed that, but if I assume alpha is a complex number, well, the slide isn't big enough. One then has to throw in, of course, doubly periodic functions, elliptic functions, integrals of elliptic functions. There are lots of meromorphic functions that satisfy these kinds of equations. So what I'm going to describe today is an approach that yields all of these results and more.
Are there anything for integral operators?
No, not yet. Let's keep it at that. So I'd like to discuss a way of looking at this. Right. Okay, so I want to talk about consistent systems. So instead of looking at linear equations, I'm going to look at systems. And we've seen that you can take a linear equation and turn it into a system. And I want a condition, not just arbitrary systems. I want a condition that, in theory, is a necessary condition for there to exist a solution. Not so interested in equations where there is no possibility for a solution. So what does consistent mean? Consistent will be the necessary conditions for the existence of a solution. And in each case, it'll look a little different. So for the experts, I'm not assuming that D1 and D2 commute. But here I am. So if you start with the operators, the derivative and the shift, well, if you have a rational function, shifting by 1 and then taking the derivative is the same as taking the derivative and shifting by 1. And if you write this equation and look at what that means for your matrices A1 and A2, it means that. So that's the consistency condition. Yes?
Existence of a solution in rational functions?
No, so
Where?
Somewhere. Somewhere.
So really on an abstract algebraic setting or formal power series? Or
Well, yeah. Yeah, so I'd like to take an extension of the rational field so that whatever relations appear for the operators continue to appear. Okay. I don't want to, I guess I could say it formally in terms of ideals and stuff. Okay. So for others, so the derivative and the Q shift, multiplication by Q, one has this relation. You know, I could change the derivative, as Julian did, but then I have more notation. So let's keep it this way. Instead of this derivative used x dx, then I again would get commutation, but let's just keep it this way. So here is the consistency condition. For two Q operators, this parenthesis shouldn't be here. This is the relation. Okay. And then in each case, you can write down what the relation is. Okay, so I want to study these. And I need a, this is the result. Consistent systems are equivalent to simple systems, and simple systems have simple solutions. That's the content of this talk. So equivalent is isomorphic as whatever category of modules you're working in. But let me spell it out. Two systems are equivalent if you can make a change of variables. You multiply on the left by an invertible matrix with rational function entries. So this is some kind of,
So here n has to be the same now? The two equations will have to be the same?
yeah, here I am assuming they're the same. But in fact, no, here I am. So, well, there are many reasons to use this as equivalent. What you're doing is if you have, let's say, a meromorphic solution of one system, you're changing it just by rational functions, not doing much to it. Turns out that when there's a Galois group involved, you're not changing the Galois group. Well, this is what equivalent means. And so what kinds of results? So here's one result that we have. So if you take a differential system and a shift system, and if they're consistent, they're equivalent to constant systems. Yeah?
When you change from the original to the simple system, do you keep the same operators?
Yes. So if you have a system like this, and you write down the condition that the derivative commutes with the shift, and the matrices obey that condition, then you can do this change of
So the
variables.
equations have both z and y?
Oh, no. Oh, sorry. This should be a z.
Okay, all right.
Okay. So, of course. So you're changing variables. Oh, that's awful. I'm sorry. But let me say it in words. A consistent system for the derivative and the shift is equivalent to a constant system. So that's in this case. In fact, this is a hard case to prove.
How about the multiplicative case?
Well, I'll go through all of them. So here's, and again, I have a y, I'm sorry. But here's the derivative in the molar. You can make this change where this is a z, where the differential equation is constant, and the molar equation, well, it has coefficients that are just Laurent polynomials. So this one is hard to prove. This one is less hard. And what I want to do is talk about the easiest case, which is the situation where you start with a differential equation and a Q difference equation. Q is not a root of 1. And my claim is that it's equivalent to a differential equation with just two singular points, one at 0 and infinity. So B is constant. And the Q difference equation is a constant equation. So these are all examples of, you start with this system. It's always with respect to the same independent variable. If they're consistent, they're very simple. They're equivalent to a simple system.
Quick question.
Yeah.
Is there a difference between lowercase gl and uppercase gl?
Yes. So this is invertible matrices, and this is all matrices.
Ah, okay, thank you.
I always thought it was the other way.
Yeah.
I don't know why.
well,
Okay, no.
this is the way it is.
All right.
Are there other questions?
So the equivalence is the hypothesis is consistent on both sides, right?
Oh, if it's consistent and you make this change of variable, it'll stay
Right,
consistent.
and the other way around. So, I mean, the hypothesis on the consistency,
Yeah.
when you say equivalent, is on what system? Which
Oh,
one of the
okay.
system?
So I start with this system with rational function
Oh, okay,
entries.
all right, okay,
It's consistent,
okay.
then it's equivalent to this other system. Okay? And this kind of a result will give you this. And I'd like to give the proof. Maybe it's obvious, but it's simple, and I'd like to give it. Okay?
Yeah, because,
So from this kind of equivalence, I get this kind of a statement. And so this is the philosophy. Consistent simple systems are equivalent to simple systems. Simple systems have simple solutions. So let me give the proof.
That's too simple.
Yeah. Since I seem to have 15 slides and I'm already on slide 9. Racing in your coffee, that's not good. Okay.
oh, of course. Just
Other
another-
questions?
Just another typo, that's all.
Yeah, sure. Tell me.
Q to the m minus 1 on the second one.
Thank you.
Is P curvature in characteristic P a consistency condition? P curvature vanishing?
So consistency with what?
So I guess P power operation and linear differential equation. So I guess a differential operator. So if you just do in one variable, it's like ddt plus a of t.
Yeah,
I don't know.
I don't-
guess
I don't
that's not.
see
Maybe
that.
you can't do that because it's just.
It's more a condition for something degenerating.
Yeah.
I don't see it, but maybe it is.
Well, yeah, the operation I'm thinking of, I guess, is not a nice operation to
Well, that's
compute
okay.
ddt plus a matrix.
Now, consistency is just the kind of weakest necessary condition that you would need with some kind of a solution somewhere.
Integrability condition?
Yeah, so we could call it integrability, and that's what some people do, but that's usually reserved for commuting
Yeah,
things.
that's true.
Yeah.
Okay. So,
Can we compute the equivalence?
can we compute the equivalence?
I mean, if we given a consistent system, the x over dy equal to a1y and y of qx equal to y2y, then you say we can
In theory, you
transfer
can.
to new one.
In-
Similar.
In theory, you can, because so by the way, I'm assuming C is an algebraically closed field, characteristic 0. So, can we compute them? I'm not sure. I was going to say you can, but I don't think that the proof gives you bounds on the gauge transformation. If you had bounds on the degrees, then yes, you could compute it, but I don't see offhand. Yeah, I'm sorry, I just don't see it. It's a good question. Uh-huh.
So in the equivalence,
Yeah.
the equivalent system, is it consistent always?
The equivalent system will always satisfy the same consistency.
So,
You have to, that's a computation.
so can you then use the condition here, like B1, B2 equals B2, B1?
Yeah,
Compute the condition of consistency on the original one.
yeah, if you knew the transformation.
Ah.
Yes.
So the same question.
Okay.
Would you need any degree bounds beyond what's known?
this transformation? Don't you have a linear differential equation that you just solve for Russian solutions?
Yeah, of course, I'm sorry. In the differential case, yeah. So, right, so it's just a, it's a parameterized differential equation. Right, so that's right.
Mm-hmm.
So yes, you do.
But you don't need to be able to compute it in order to know the actual transformation to state the condition on the original system that they're consistent coming
right.
from the other one.
Yeah, I'm not sure. So you're saying that if you start with this,
Right.
and you say you know there exists a transformation,
That's right. To turn into that one.
then
Then how do you state that consistency equivalence without actually evolving the transformation?
yeah, no, I mean it's a condition on A1 and A2. I'm
That's
not
right.
sure I understand.
That's right. So can you do that? I mean, can you state the that
Yeah,
condition?
right.
Oh,
it's
okay.
it's the condition that when you shift, what I had written down before.
Oh, right. Okay.
Yeah. Thanks.
Sorry.
Okay. Let me prove it just to show you what the those conditions are. So I want to prove the corollary from the theorem. So I'm going to let V be the C of X vector space generated by the various these guys, the Fi, Q, J, X, Ex. So F is this Laurent series that satisfies this. Now, if you think about this for a second, this is going to be finite dimensional. And you just use these equations. If you differentiate this enough times, you can use this to get the higher derivatives in terms of the lower. So this is some finite dimensional vector space. And I'm going to let G1 to G M. M is a bad letter. M the basis.
I means the power.
So this is the next derivative.
Okay.
And so since this is a basis, this will be, V is also invariant under D, well, for this reason as well. And the shift, let's say sigma Q, V is in V. So I will get two equations for my G1 and Gn. And sigma Q this. And it's a computation to check that they're consistent. Okay, so now my theorem says I can make a change of variables. So if I let's say, let y be this vector, and z be my change of variables. Okay. This is still a basis. And z will satisfy a very simple system. Y there, so z x is d1 x, and z qx is d2 So I'm going to use that. And now I'm going to forget about the differential equation. That's interesting. I'm going to just look at, so my z, this is a column vector. So I'm going to write it as zi x to the I. Zi is just some column vector of constants. Right? Because my vector space V just consists of Laurent series. So what happens here? I look at z of qz, that's z to the I, q to the I, x to the I. And this is, now B is a constant matrix. What's this? And if we look at these coefficients, what am I saying? I'm saying that zi is a q to the I eigenvector of B. And now q is not a root of unity. So all those q to the I are different. And the matrix has only a finite number of non-zero eigenvectors. So this zi is zero almost everywhere. So in particular, the entries in my z are in fact Laurent series, they're rational functions. They were a basis. So there can really only be one of them. N is 1. This guy is 1. This vector space is just the one-dimensional vector space over C of x, so everything in it is rational. People don't mind me giving proofs, but when they're simple, they're sometimes instructive. The point is, a result like this will always give you results like this. So you get a result like this for two different operators, and you'll be able to say something at the end. It may not be this, it may be that it's a C of x combination of exponential functions, but it will be something. Okay. So I gave you the motivation. I talked about linear equations. I talked about systems. And now I want to continue to give you some idea of the proofs. So let me restate my philosophy again. That is that consistent systems are equivalent to simple systems. And so the proof is along the following lines. I'm going to show that I get an equivalence to simple systems because consistent systems have simple singularities. I'll tell you what a simple singularity is. These are not technical terms. Consistent systems have simple singularities because they have many symmetries. And the symmetry, yeah. So when you have something that has lots of symmetries, it can't be too complicated. And here's the key idea. This is an idea that appears in several places. I think it also occurs in a paper that Alexei and Mikhail wrote. What is the meaning of this consistency condition? So I kind of beat you into believing that the real meaning is that you might have a solution. But in fact, since we're talking about differential algebra, we don't like to talk about solutions, right? We like to talk about equations. So the real meaning is that you start with this system to say that this difference equation, the Q-difference equation, is consistent, says that this original equation is now equivalent to a new equation. And the equivalence is given by the second equation. So let me say this in a different way. The differential equation for y of x is equivalent to the differential equation for y of q of x. So the consistency condition says that you're getting an equivalence between a differential equation and another differential equation. And I think in your paper with Mikhail, you replace integrability conditions with this notion that something is, that two modules are isomorphic. So it has the same flavor. Anyway, so I'm going to use this fact. That is, here's a differential equation for this guy. If I take this guy and multiply it by a matrix of rational functions, I'm going to get this guy. That's a very strong condition. And it turns out it's a condition that when you look at the singular points, it says they really can't be too bad. Okay, let me tell you about singular points. Just the differential equations. So this was the missing piece in the last talk. So there are lots of ways of talking about singularities. There are ways of doing it without talking about solutions. But I think you see it, the easiest way to see it is to talk about solutions. If you start with now I'm starting with a differential equation and I'm looking at it locally. So I'm assuming that the entries are power series, Laurent series. We can always solve such a system in general. The solution looks like this. There's, first of all, an n by n matrix whose entries are power series not in x, but in roots of x. Then you have x to some matrix. And you have this exponential term. And the exponential term in the exponent is a diagonal matrix. On the diagonal are polynomials in powers, negative powers of x, negative rational powers of x. So for instance, you can think, well, e to the minus e to the minus x, something like that, or e to the minus the square root of x. So this is the general solution of such an equation. And you could try and, there are many ways of writing this. I can make the various terms unique by specifying certain things, but without too much specification, the exponential part is unique up to permutation of the diagonal. That is, you could write another solution this way with these properties. If you look at that exponential part, the only difference will be you'll have permuted the diagonal elements. That's something I'm going to use. So this is the most general solution. If there's no exponential term, the exponential term doesn't occur, then you get what's called a regular singular point. And if you start with convergent entries in A, you'll get that your solution is convergent. I say in sectors because you may have roots of x. If you don't have roots, it's convergent. And if you have a regular singular point, it's always locally equivalent to just a very simple kind of singularity. E over X. And there are other ways of describing this, but I just want to look at this. Then there are singularities that really shouldn't be singularities. They're removable singularities.
We're talking about at zero.
Excuse me?
We're talking about at the point zero.
This is local. I'm just looking at this.
You're assuming there is a singularity at zero. This is,
Yeah. So should I call something singular if it's not
I think you're
singular?
assuming that there's a singularity at zero and you're describing when it's regular, when it's root central.
Right. Yeah, okay. So a removable singularity. So regular was Q was 0. Now if I let L be 0, I'm just saying there's a formal solution. Well, I'm working locally. If there's a formal solution, I can make a change of basis so that the solutions are constant. That is, I use Y as my change basis, and I'll get things are equivalent to this. And again, things will be convergent as long as you start with convergent things. So removable singularities, there's this notion of an apparent singularity, and it's a word I don't particularly like, but removable, you actually could have a singularity. That is, this equation could have a rational solution, could have a pole at 0. So this is the hierarchy of singularities, and of course, you could then have no singularity. Did I say that? Yeah, non-singular. So
What would be the meaning of x to the L? It's just
x to the L, e to the L log x. Okay. Don't look at this too carefully. I could form a differential field in which all of these make sense, and I don't want to assign them analytic meaning right now. Okay, am I?
So having a single solution in the ground field implies it's trivial. What that saying?
Yeah.
A single solution, a single.
So it's a matrix, right?
No, vector matrix.
These are matrices.
Y is a matrix.
Y is a matrix.
Okay, we're on GLM.
Yeah,
We're
right.
on GLM.
Yeah. So if you have a full set of solutions in the ground field, it's a trivial equation.
So when you say y-x convergent in sectors, you mean, right? I mean,
Well, here actually, let's see. Here it's going to be just convergent.
okay.
As a meromorphic function.
Right.
You'll have in the punctured disk.
But I mean, in the regular singular case, it was, I mean, you're talking about rays, or you talking about?
This was just because I could have square roots and I
Right,
wanted
okay.
to be careful.
Okay. Sorry. All right.
And up there, definitely you get situations where things are not convergent.
Right, okay.
Yeah.
Okay?
And, I have a question. So
Yeah.
where did the 1 over R go?
Where did the 1 over R go?
Oh.
There's no 1 over R.
Yes, there is. Formal solution in x equals 0.
Yes, we're taking roots.
Yeah, so it's there.
Yes, and
Yeah.
and it doesn't appear here.
So meaning that it's a here.
Yeah.
The power series in x.
So this Y still could have
Ah.
this Y could still have roots.
And what about the next
The next
case?
line.
In the next case, not.
It's
You still have one.
theory.
I'm sorry. In the next case, too. In this case,
No.
what am I
Oh,
saying?
wait.
No, the next case.
So now I actually say
Oh, right.
this is in here.
But you say it implies, so it's some theorem to prove, right? So it implies. It's
Yeah,
implies.
right,
It's
right.
not like a.
Right. So this, I'm not stating this in that,
Special case, they're all special cases.
that these things are logical consequences of the others. This situation, this happens. Okay. Good. More questions? More typos? Okay. So I'm looking at this equation now. So this, I claim, is this is the simplest case I can explain. So I'm starting with this consistent system, A1 and A2. A1 is just a matrix with rational function entries. A2 is an invertible matrix with rational function entries. And I'm assuming consistency. So the consistency says that the differential equation for y of x is equivalent to the differential equation for y of q of x. That's what the consistency condition means. So I claim that this implies that all the finite singular points except for 0 are removable, meaning that you have meromorphic solutions there. And at 0 and infinity, you have at worst regular singular points. So this is the claim, and I'm going to prove it again.
Okay, A1 and A2 are lower series?
No, now these are they have rational function entries so that I can talk about solutions in other places. Yeah? So now I'm So all singular points are removable. So I have this statement there. It's easy induction. You can show that your original equation is equivalent to an equation like this. Just keep going. So what's the point here? So the singular points of an equation are places where the denominators vanish. So let's say the singular points here are alpha 1, alpha n. The singular points here will be q to the minus n alpha 1, q to the minus n alpha n. And for n big enough, these two sets are going to be empty. And again, here I'm using, q could have absolute value 1, but it better not be a root of unity. So for large n, large enough n, or for some n, I can push these things apart. Okay, so what does that mean? So these are equivalent. I take a solution here that's analytic at these points. I multiply it by a matrix with rational entries, and I get a solution here. So I've taken something that's analytic, multiplied it by some rational function. So it, at worst, has a pole. At worst, it has a pole. So that's here. I could do it in the opposite direction. I could take something analytic here, multiply it by a rational function, At these points, it will have at worst a pole. So it will have a basis of solution